Students, welcome to math practice. Today we are going to do sets or set theory. This is a very interesting topic and this is a one-shot video of set theory. It covers all the important topics with examples. So watch the video till the end. First we are going to discuss all the theoretical aspects of sets. A set is a well-defined collection of objects known as elements or members of the set. For example, you can have set of positive integers, you can have set of tables in the given room, you can have the set of students in your class. So set is any well-defined collection of objects. Now some standard sets in maths are, these are very useful, so remember them. Set of natural numbers, which is 1, 2, 3 and so on. It is denoted by n. Set of whole numbers, w. It is 0 and natural numbers means 0, 1, 2, 3, 4 and so on. Set of integers, negative, minus 3, minus 2, minus 1, 0, 1, 2, 3. So it is negative numbers and whole numbers. Set of rational numbers, it is all the numbers of the form p by q where q is an integer and q is not equal to 0. For example, I have the set of fractions half, 1 by 4, so they are of the form p by q. Set of irrational numbers, set of all those x such that x is not a rational number. So all the numbers other than rational numbers will be irrational numbers. And set of real numbers is the set of rational numbers union set of irrational numbers. In addition to this, you can also have set of complex numbers. First thing is, how do you represent a set? A set can be represented in two ways. First is the roster or tabular form and second is the set builder form. In roster form, all the elements are listed and separated by commas and are enclosed within brackets, curly brackets. For example, the set of all even positive integers less than 7. Suppose if I want to write in roster form, it is written as 2, 4, 6. In roster form, the order in which elements are listed is immaterial. Like for example, in the previous case, I can also write the set as 4, 2, 6. Also, while writing the set in roster form, an element is not repeated. For example, the set of letters forming the word school. It is the set consisting of S, C, H, O, L. And you can also change the order. Second way of representing a set is the set builder form. Here all the elements of a set possess a single common property which is not possessed by any element outside the set. For example, if I have the set A, E, I, O, U, it is the set of all the vowels of English alphabets. And no other letter possesses this property. So we can write it in set builder form as set V is equal to set of all x such that x is a vowel in English alphabet. It may be observed that we describe the element by the set by using a symbol x. Anything you can use x, y, z, anything. And then we have a colon. And then after that you write the property which it follows. For example, if I want to write the set of all even positive integers less than 7, in set builder form I can write it as x such that x is an integer means x belongs to set. X is even and x is between 1 and 7. So 1 less than x less than 7 in curly brackets. Some other important definitions. Different types of sets. Finite set. A set is finite if the number of elements in it is finite. And infinite means it is infinite if the number of elements in it is not finite. Right? For example, if I have the set of integers between 1 and 20, then it is a finite set. But if I have just the set of integers, then it is infinite set. Empty set, null set or void set. It means the set does not contain any element. For example, if there is a room in which there are no chairs and if you define the set of chairs in that room, it will be an empty set. Singleton set, a set containing only one element. Equal sets, two sets are equal if they have the same elements. The elements should be same. Equivalent sets means if they have the same number of elements. Power set, the set of all possible subsets of a set A is its power set and it is denoted by P of A. We will see all the examples after this. That means suppose if I have the set which has numbers 1 and 2, what will be its subsets? Its subsets will be the set containing just 1, the set containing 2, the set containing 1, 2 both, and the null set. Remember, null set is a subset of every set. Universal set, a set that contains all the elements including itself, is a universal set. Suppose if I have the set of integers between 1 and 10 and it is defined on the whole set of integers, then the whole set of integers can be the universal set in this case. Subset. When all the elements of a set A belong to a set B, then A is called the subset of B. If the set A has 1, 2, set B has 1, 2, 3, I can say A is a subset of B. Proper subset, A is a proper subset of B if A is a subset of B and A in any case is not equal to B. So if I have A is equal to 1, 2 and B is also equal to 1, 2, I can write A as a subset of B, but A is not a proper subset of B. Now there are some operations which are defined on sets. Remember, we are going to see all the examples for these concepts. So just now we are just defining the concepts. Union of sets. Union of two sets A and B is denoted by A union B, and it is a set of elements which are in A, in B, or in both A and B. Intersection. Intersection of sets A and B is denoted by A intersection B, and it is a set of elements which belongs to both A and B. It should compulsorily belong to both A and B. Disjoint sets means two sets are disjoint if their intersection is the empty set, means they do not have any common element. Difference of two sets, it is denoted by A minus B, and it is the set of all those elements of A which do not belong to B. A minus B means set of all those elements of A which do not belong to B. Symmetric difference, this is a new concept. The symmetric difference of sets A and B, it is denoted by A triangle B, and it is defined as A minus B union B minus A. Complement of a set, the complement of a set is the set of all those elements which are in the universal set but not in the set A. For example, the universal set consists of integers from 1 to 10, and set A consists of all the even integers from 1 to 10. Then the complement of A will have all the odd integers between 1 to 10. Now some formulas which you need to remember. Cardinality of a set, or the cardinal number for a set, is the number of elements in the set A, and it is denoted by n of A. Remember, when you are writing a set, you don't repeat the elements. So all the elements are distinct, and the total number of distinct elements in the set is denoted by n of A. Now remember, for any two sets A and B, you can always check it out. N of A union B is equal to n of A plus n of B minus n of A intersection B. Means the elements which are in A union B is equal to the elements in A plus the elements in B minus the elements which are in both A and B. Similarly, you extend it, n of A union B union C is n of A plus n of B plus n of C minus n of A intersection B minus n of B intersection C minus n of A intersection C plus n of A intersection B intersection C. Same way, from the first case you can also write n of A intersection B is n of A plus n of B minus n of A union B. N of A minus B is, remember, all the elements which are in A but which are not in B. So A and n of A union B minus n of B. You can also write it as n of A minus n of A intersection B. And this you will be able to prove once you understand the concept. N of A symmetric difference B is number of elements in A plus number of elements in B minus 2n, means 2 into number of elements of A intersection B. You already know some properties for different operations like addition, subtraction. Similarly, for sets also you have the properties. First is a commutative property. It means A union B is always equal to B union A. Same way A intersection B is B intersection A. Associative property, when you take three sets together and when you interchange the position of the bracket, the sets will remain the same. Distributive property, A union B intersection C is A union B intersection A union C. Similarly, A intersection B union C is A intersection B union A intersection B C. Remember over here, when you apply the distributive property, the sign which is outside the bracket is reverse. That means union turns into intersection, intersection turns into union. Identity property means when you take the union of any set with the null set, obviously you will get the same set. So A union null set is A. And when you take the intersection of any set with the universal set, because universal set is the whole set on which a set is defined, so its intersection will be the set itself. Complement, A union A complement will give the universal set. As I told you before, if your universal set is a set of positive integers between, if your universal set is a set of even positive integers between 1 and 10, then the complement is odd positive integers. So when you take the union, you will get all the integers which are between 1 to 10. Idempotent property, it means A intersection A will always be A and A union A will always be A. Next you have the DeMorgans law. The first two DeMorgans law are very important, which we will be using in the examples. A union B complement is A complement intersection B complement, and A intersection B whole complement is equal to A complement union B complement. Now the other results will follow from these two results. You can always check by taking examples. So remember, the first two laws, which are called the DeMorgans laws for union and intersection, are used frequently. Now some things to remember before we go to the examples. The total number of subsets of a finite set containing n elements is 2 raised to n. That means if your set contains n elements, the total number of subsets it will have is 2 raised to n. The set of all subsets is called power set. So the power set will contain 2 raised to n elements. Hence the total number of proper subsets of a finite set containing n elements is 2 raised to n minus 1. Remember, this type of thing can be asked as a objective question. What it simply means is that a set will consist of 2 raised to n subsets. Now from that, one subset will be the set itself. So if you want the proper subset means it should not be equal. So if you want the proper subset, the total number of proper subsets will be 2 raised to n minus 1. Now for example, find the number of proper subsets of the set of first 4 even natural numbers. First 4 even natural numbers are 2, 4, 6, 8. How many subsets it will have? It will have 2 raised to 4, means it will have 16 subsets. But you want the proper subset, means from that subsets, the set itself 2, 4, 6, 8, that we take out. So it is 2 raised to n minus 1 or 16 minus 1, which is 15. So the set 2, 4, 6, 8 will consist of 15 proper subsets. Now we will start with the examples. All the concepts of set theory will be clear if these examples are understood. First one, which of the following are sets? First of all, let us justify whether which of the following are sets. The collection of all months of a year beginning with the letter J. Yes, we know there is no month which begins with J, but you can also have an empty set. So you can say it is a set. Second, the collection of 10 most talented writers of India. No, it is not a set, because here the opinion is subjective. All the people can have different opinions. So it should have fixed members. It is a well-defined. Remember the definition, well-defined collection. A team of 11 best cricket batsmen of the world. Here also the concept is subjective. So it is not a set. The collection of all boys in your class. Yes, it is a set. The collection of all natural numbers less than 100. Yes. The collection of novels written by the writer Munshi Premchand. Yes, that is also a collection of, it is a collection of novels which is a set. Why? Because it is well defined. You know which novels the author has written. The collection of all even integers, it is a set. Collection of questions in this chapter, yes, it is a set. A collection of most dangerous animals of the world, this is not a set because here also the opinion is subjective, it is not well defined. Second question, write the following sets in roster form. We know there are two representations, roster form and set builder form. Now here the set builder form is given and you have to write in the roster form. Set A consists of all such x such that x is an integer and x is between -3 and 7. So all the integers between -3 and 7. So A is equal to -2, -1, 0, 1, 2, 3, 4, 5, 6. B, set of all x such that x is a natural number less than 6. Natural number starts with 1, 2, 3, 4 and so on. So B is 1, 2, 3, 4, 5. C, set of all x such that x is a 2-digit natural number such that the sum of its digits is 8. 2-digit numbers whose sum is 8. So which are they? As listed, 17, 26 up to 80. D, set of all such x such that x is a prime number which is a divisor of 60. You know that there are many divisors of 60. Like you have 1, 2, 3, 4, 5, 6, 10, 15, but from that you want a prime number, correct? So which are the prime numbers? 2, 3 and 5, they are prime numbers. So remember 1 is a special number, so it starts with 2. D is equal to 2, 3, 5. 2, 3, 5 are the only prime numbers which are divisor of 60. E, set of all letters in the word trigonometry. Remember, if a letter alphabet is repeated, you don't write it again in the set. So E is equal to set which consists of elements TRIGONMEY. F, the set of all letters in the word better. Here also F will consist of B, E, T and R. Next, write the following sets in the set builder form. So now first set is 3, 6, 9 and 12. So how can we write it? When you just look at the numbers, it is very clear that it is 3, 3 into 2, 3 into 3, 3 into 4. So it is a set of all such x such that x is equal to 3n, where n is a natural number and n is between 1 and 4. 1 less than or equal to n, less than or equal to 4. Second one, 2, 4, 8, 16, 32. Here you can see it is a square. It is a different powers of 2. 2, 2 raised to 2, 2 raised to 3 and so on. So x is equal to 2 raised to n, where n is a natural number and n is between 1 and 5. 5, 25, 125, 625. Similarly here x such that x is equal to 5 raised to n, n belongs to n, 1 less than or equal to n, less than or equal to 4. Which of the following are examples of the null set? Null set means the empty set or the void set. Set of odd natural numbers divisible by 2. You do not have any odd natural numbers which are divisible by 2. All the even numbers are divisible by 2. Second one, set of even prime numbers. It is not a null set. Why? Because you have the number 2 which is prime. So it is even and it is prime. So this set is not an empty set. Set of all x such that x is a natural number such that x less than 5 and x greater than 7. It is not possible x less than 5 is 1, 2, 3, 4 and greater than 7 means 8, 9 and so on. So this set is not possible that you have a number which is also less than 5 and also greater than 7. So it is a null set. Set of all y such that y is a point common to any two parallel lines. When the lines are parallel, they will not have any point in common. So this is a null set. Which of the following sets are finite or infinite, you have to say. First one, the set of months of a year, obviously finite. 1, 2, 3 and so on. All this, the set of natural numbers, basically it is infinite. Set of positive integers greater than 100. You can have infinitely many positive integers greater than 100. Set of prime numbers less than 99. Yes, it is finite because prime numbers less than 99. So you can have it as starting from 2. You can have all the prime numbers which are less than 99. The set of circles passing through the origin 0, 0. Obviously from any point infinitely many circles can pass, so it is an infinite set. Next question, are the following pair of sets equal? You know two sets are equal when they have the same elements. So first one, A is equal to 2, 3, B is equal to set of all x so that x is a solution of x square plus 5x plus 6 is equal to 0. This is a quadratic equation, so you have x plus 2, x plus 3 is equal to 0, means x is minus 2, x is minus 3. So obviously both sets have different elements, they are not equal. Second one, A, x is such that x is a letter in the word follow. Which are the letters? Distinct letters F, O, L and W. Same way B, set of all y so that y is a letter in the word wolf. So that is also W, O, L and F. So both have same elements, A equal to B. Third one, A, set of all integers 2, 4, 6, 8, 10 and B is set of all integers which are positive and even. So x is positive even integer and x is less than or equal to 10. So B will also consist of 2, 4, 6, 8 and 10. So both are having same elements, A equal to B. Next question, you have to say whether following statements are true or false. Before that, remember, when you are comparing two sets, you generally write it is either a subset or it is not a subset. But when you are writing an element always belongs to a set. Element is not a subset of a set. Element always belongs to the set. First one, A set consisting of A, B is not a subset of set consisting of A, B and C, which is obviously false. Set consisting of A and E is a subset of set of all x, so that x is a vowel in English alphabet. So the right hand side consists of A, E, I, O, U. So set consisting of A, E is a subset of set consisting of A, E, I, O, U. So that is true. Third one, set consisting of elements 1, 2 and 3 is a subset of set consisting of elements 1, 3 and 5. Obviously false. Fourth one, set consisting of just the element A is a subset of set consisting of elements A, B and C. This is true because you are comparing two sets. But the fifth one is false. Why? Because it is written set consisting of element A belongs to the set consisting of elements A, B and C. Belongs to will always be for element. So if it was written without the curly bracket that A belongs to the set consisting of A, B and C, it would have been true. Sixth one, x, so that x is an even natural number less than 6. So you have even natural number which is less than 6, means it is 2, 4, 2 and 4. It is a subset of set of all x such that x is a natural number which divides 36. Correct? There are many natural numbers which will divide 36. Like you have 1, 2, 3, 4, 6, 12, so on. You will have up till 36. So obviously the set on the left hand side is a subset of set on the right hand side, because right hand side obviously consists of 2, 4. Next question. Let A is equal to set of elements which are 1, 2, 3, 4, 5. Which of the following statements are incorrect and why? Now just remember, here the set A consists of 4 elements. 1, 2, 3, 4 is considered as an element and 5. First thing is 3, 4 is a subset of A. As I told you, an element is never a subset, an element belongs to. So first statement is false, but the second statement is true. 3, 4 is an element which belongs to set A. Third one, a set which consists of the element 3, 4. There is a set which consists of just one element, which is 3, 4. Is a subset of A. It is true because set is always a subset, can always be a subset of another set. Fourth one, 1 belongs to A. Yes, true. 1 is a subset of A. Again false. The set consisting of 1, 2 and 5 is a subset of A. True. Set consisting of 1, 2 and 5 belongs to A. Again false because set is a subset, element belongs to. 1, 2, 3 is a subset of A. False because 3, there is no such element which is just 3. Null set belongs to A. False. Null set is a set. So a null set is a subset of A, which is true. The set consisting of null set is a subset of A. Again, this is false. Next question. Write down all the subsets of the following sets. Before that, let me remind you that if a set has n distinct elements, the total number of subsets which it will have is 2 raised to n. First one, there is a set which consists of just one element A. That means n is equal to 1. So 2 raised to 1 means it will have two subsets. One is the null set and the set itself. Second case, suppose if a set has two elements A and B, then 2 raised to 2 means 4. Which are the subsets of it? Null set and the set itself. That means null set and the set consisting of AB. In addition to that, just the set consisting of just element A and set consisting of just element B. So these are the subsets. Subsets of 1, 2 and 3 are 5, set consisting of 1, set consisting of 2, set consisting of 3, set consisting of 1, 2, then set consisting of 2, 3, set consisting of 1, 3 and the set itself which is 1, 2 and 3, set consisting of 1, 2 and 3. Only subset of null set is null set. Now if there is a empty set, it's only one subset which is null set. Write the following as intervals. Now any set, if it is numerical in this manner, you can write it as an interval. Close interval means that particular number is included. Open interval means it is not included. Set of all x such that x belongs to R minus 4 less than x less than or equal to 6. Since on the left hand side minus 4 is not included, all the real numbers which are greater than minus 4 are included. So it is you just have the round bracket. Now on the right hand side 6 is included, so you have the square bracket. Next case, minus 12 less than x less than minus 10. So here you just have less than sign on both the sides, so it is round bracket. Third case, 0 less than or equal to x less than 7. That means 0 is included, 7 is not included. So square bracket 0 and it ends with the round bracket for 7. Fourth one, 3 less than or equal to x less than or equal to 4. So it is in the square bracket. 3, 4 is in the square bracket. Next interesting question. If set A consisting of 3, 5, 7, 9, 11, B consists of 7, 9, 11, 13, C consists of elements 11, 13 and 15 and D consists of elements 15 and 17. You have to find the following, you have to do the following set theoretical operations. A intersection C intersection D. Since it is associative, you can take any two first and then the third one. So suppose A and C, first of all when you take A intersection C, it consists of element 11. Intersection with D which is 15 and 17. So there is no such element which belongs to A, C and D, all the three. So it is null set. A intersection B union C. So you can do it in two ways. Either you first find B union C and take A intersection with that, or you can use the distributive property. What is the distributive property? A intersection B union C is A intersection B union A intersection C. So if you do in that manner, A intersection B is 7, 9, 11 and A intersection C is just 11 and the union of both of them is 7, 9, 11. Third one, A intersection B union C. So first of all, A intersection B is 7, 9, 11 and B union C is 7, 9, 11, 13 and 15. B union, now what you have to do is you have to take the intersection of both of them. So intersection of both of them consists of common elements 7, 9, 11. Fourth one, A union D intersection B union C. A union D is listed, B union C is listed. Now which are the common elements in both of them? 7, 9, 11 and 15. Fifth one, A minus B. I am repeating again, A minus B means set of all those elements which are in A but which are not in B. So which elements are there which are in A but which are not in B? They are just 3 and 5. 7, 9, 11 are also there in B. So A minus B is 3 and 5. You can also interpret A minus B as A intersection B dash, means set of elements which are in A, and intersection stands for and, union stands for or, and which are not in B, that means B complement, correct? Same way B minus A, set of elements which are in B but which are not in A. So only element 13 is there which is in B but which is not in A. Are the sets B and D disjoint? Yes, B and D disjoint means the intersection is null set. So you can see B and D, their intersection, B and D if you take 7, 9, 11, 13 and here D is 15, 17. So their intersection is null set. Note that every set is disjoint from the empty set. Obviously, when you take the intersection with empty set, then the answer is always null set. That means every set is always disjoint from the empty set. Next question. Taking the set of natural numbers as the universal set, write down the complements of the following set. So set N, set of natural numbers, is our universal set. If there is a set of X such that X is an even natural number, its complement of this set, remember it is denoted by dash. You have a dash as the superscript. So the complement of this set X is an even natural number will be set of all such X such that X is an odd natural number. Second one, set of all X such that X is a positive multiple of 3. Obviously its complement is X is not a multiple of 3. Correct? Because you cannot have a negative multiple, because it is the universal set is a set of natural numbers which does not include negative numbers. So it is just set of all X such that X belongs to N and X is not a multiple of 3. Third one, set of all X such that 2X plus 5 is equal to 9. When you solve it, X you get it as 2. So its complement will be X should not be equal to 2. So set of all such X such that X belongs to N and X is not equal to 2. Fourth one, set of all X so that X is greater than or equal to 7. Complement of this set will be greater than or equal to 7, means less than 7. Or you can also write it as 1, 2, 3, 4, 5, 6. You can write it in any form. Fifth one, set of all X so that X belongs to N and 2X plus 1 greater than 10. That means when you solve 2X plus 1 greater than 10, your X is greater than 9 by 2. So its complement will be set of all N such that X is less than or equal to 9 by 2. If you have to list the elements of this set, which will be the elements? 9 by 2, that means it is 4.5, but it is a set of natural numbers. So it will be 1, 2, 3 and 4. Note that your U is equal to N, which is a set of natural numbers. If U is equal to set having elements 1, 2, 3, 4 up till 9, A has elements 2, 4, 6, 8 and B has elements 2, 3, 5, 7, verify the DeMorgans law. The DeMorgans laws are for union and intersection. A union B complement is equal to A complement intersection B complement, and A intersection B whole complement is A complement union B complement. It is very simple. Universal set is given. So first of all, what you do is, first you have to verify A union B complement. What is A union B? First of all, 2, 3, 4, 5, 6, 7, 8. And its complement will be the remaining elements, which are 1 and 9. Because our universal set is 1 up till 9. Now what is the right hand side? A complement intersection B complement. A complement is 1, 3, 5, 7, 9 and B complement is 1, 4, 6, 8, 9. Its intersection is 1 and 9. So both are equal. So we have verified. Similarly, you can verify the second DeMorgans law. Next example. In a group of 400 people, 250 can speak Hindi and 200 can speak English. How many people can speak both Hindi and English? In a group of 400 people, so we know over here that the 400 people which are taken over here can speak either English, either Hindi or both the languages. So suppose H is a set of people who speak Hindi and E is a set of people who speak English. So what is given to us is totally 400 people who speak any of the languages. So H union E is 400 number of elements. Same way number of elements in H is 250, number of elements in E is 200. We use this formula N of number of elements of H union E is number of elements of H plus number of elements of E minus number of elements of H intersection E. Put the values, so we get number of elements in H intersection E as 50. H intersection E means speaking both the languages. Once again, remember intersection means and union means or. So 50 people can speak both Hindi and English. Next example, in a committee 50 people speak French, 20 speak Spanish and 30 speak both Spanish and French. How many speak at least one of these two languages? At least one of these two languages means Spanish or French. That means Spanish or French means it can consist of Spanish, French, or both of them. So what we have to find is S union F. At least one means, always remember, S union F. Again, by the formula, n of S union F is n of S plus n of F minus n of S intersection F. We are given the values, just put the values, you get the number of elements in S union F as 60. Means 60 people in the committee speak at least one of the two languages. In the next example, it is said that show that the following four conditions are equivalent. The four conditions are A subset B, A minus B is the null set, A union B is B, and A intersection B is A. It is very clear that all the four statements are equivalent. Now remember, when you want to prove anything, any statements are equivalent, there are two ways to prove here. Either you prove that 1 double implies 2, 1 double implies 3, and 1 double implies 4. Or you can prove 1 double implies 2, 2 double implies 3, and 3 double implies 4. Anything can be done. So first of all, we prove that 1 double implies 2, means 1 implies 2 and 2 implies 1. We want to prove 1 implies 2 means let us assume that A is a subset of B. Now we want to prove A minus B is the null set. If possible, assume A minus B is not the null set. That means there exists some element X such that X belongs to A and X does not belong to B. What is A minus B? Elements which belong to A but which do not belong to B. So X belongs to A but X does not belong to B. But since it is given A is a subset of B, if X belongs to A, obviously X belongs to B. So our assumption is not possible. That means A minus B is null set. So we have shown 1 implies 2. Next, assume that A minus B is null set and we want to prove A is a subset of B. Let X belongs to A. So X belongs to B. Why? Because if X does not belongs to B, that means A minus B cannot be empty set. Once again, A minus B, elements which are in A but which are not in B. So if X does not belong to B, then A minus B cannot be null set. Hence A minus B is null set, implies that A is a subset of B. So we have shown that 2 implies 1 and hence 1 double implies 2. In the next part, we will prove that 1 double implies 3. That means assume that A is a subset of B. That means all the elements of A are in B. So obviously it is clear that A union B will be B because all the elements of A are in B. So their union will be equal to B. Now in the second case, let us assume that A union B is B. If A union B is B, that means B contains A, or you can say in other words that A is a subset of B. So 1 double implies 3. Now to prove that 1 double implies 4, again first of all assume that A is a subset of B. That means there is no such element X such that X belongs to A but X does not belong to B, because every element of A belongs to B. Hence A intersection B will be A because every element of A belongs to B, so their intersection will be the set A itself. Next, to prove the converse part, assume that A intersection B is equal to A. That means every element of A is in B because their intersection is the whole set A. So every element of A has to be in B. So it means A is a subset of B. So we have shown that 1 double implies 4. Hence all the 4 conditions are equivalent. Next interesting example. Now remember, there is a technique to solve the set theory examples. You can solve it by drawing the Venn diagram. Venn diagram means representing a set in the form of a circle. So let us see how easy it becomes when you can represent the problem in the form of Venn diagram. In a group of 100 people, 76 drink tea and 43 drink coffee. You have to find some things. So first of all, you have people drinking tea, let that be T, and the set of people drinking coffee, let that be C. So draw 2 circles. Now since you can have people which drink tea and coffee both the circles will intersect and look as shown in the figure. So first of all, what is given to us is 76 people drink tea and 43 drink coffee. That means N of T is 76, N of C is 43. And the union total is 100. So we have A union B is equal to A plus B minus A intersection B. Similarly over here 100 is equal to 76 plus 43 minus the number of elements in T intersection C. So when you solve it you get it as 19. So there are 19 people who drink both tea and coffee. You can also verify that, see over here 19 people drink both tea and coffee. Total 76 drink tea. So how many people drink just tea? That means just tea means 76 minus 19, which is 57. And how many people drink just coffee? Total people who drink coffee are 43. Out of that 19 drink both of them. So 43 minus 19, which gives you answer 24. So from the Venn diagram it becomes very easy to solve the example. Next example. Let the universal set be set of all natural numbers such that they are between 1 and 10, 1 and 10 included. If A has elements 1, 2, 3, 4, B has elements 2, 3, 6 and 10, what is the complement of A minus B? So first of all, what is A minus B? Set of elements which are in A but which are not in B. So 1 and 4 are in A but they are not in B. Complement of this set means a universal set minus the set will give you the complement. So which are the elements in A minus B complement? 1 to 10 minus 1 and 4, that means 2, 3, 5, 6, 7, 8, 9, 10. Next example, see we are trying to cover different type of examples to make the concept clear. Suppose the elements in the universal set are 800, elements in set A are 250, set B 300, A intersection B 350, then find number of elements in A dash intersection B dash. Now see, we are going to, whenever it is given in this manner, you know that A dash intersection B dash is A union B whole dash by DeMorgans law. So first thing is you find N of A union B, that is equal to N of A plus N of B minus N of A intersection B. Hence you have got number of elements in A union B as 200. By DeMorgans law, N of A dash intersection B dash is N of A union B whole dash. That means number of elements in universal set minus the number of elements in A union B. Complement means universal set minus the set. So 800 minus 200, which gives you 600. Next example. In an examination out of 100 students, 75 passed in English and 60 in maths. Also 45 students passed in both the subjects. Find the number of students who passed in exactly one of the two subjects. Again here Venn diagram becomes very helpful. So total there are 100 students, 75 pass in English and 60 pass in maths, and 45 students pass in both the subjects. So first of all, when you draw the diagram, in the intersection part there are 45 students. 75 passed in English. So 75 minus 45 means 30 students are there who just passed in English. Similarly, when you draw the diagram, it is given 60 pass in maths. So 45 pass in both of them. So 60 minus 45. Only 15 students. There are 15 students who pass in only maths. So now find the number of students who pass in exactly one of the two subjects. Exactly one of the two subjects means either the person has passed just in English or just in maths. So how many people? 30 plus 15, which is equal to 45. See students, set theory is a very interesting topic, and in this video we have covered all the concepts of set theory with the help of examples. In case of any query, please write in the comment section. Do like and share the video and subscribe to Math Practice for many such other videos on maths.